All right, so the other day after the lab, we formalized an understanding that you guys were developing, where we said, look, if you want to calculate the momentum of an object, you just multiply the mass times velocity. No big deal. It's a kind of a mathematical expression, but has like this conceptual understanding that the momentum is how difficult it is to bring an object to a stop. Now, if you want to change the momentum, what's going to happen is you're going to end up changing the velocity, because the object still has the same mass. So if you change its momentum, its velocity is going to change. No big deal. Now, how do you actually change the momentum of an object? Well, you need to apply a force, and that force has to last a certain amount of time. Okay? So if you want to change the momentum of an object, you need to apply a force, and that force needs to last a certain amount of time. Does that make sense? Yes?
I would say a good example of that would probably just be a car going down a hill.
Yeah, I mean, think about a car going down a hill. You have a gravitational force on the car, it's rolling down the hill over a certain amount of time, you're going to get the mass is going to change its velocity, right? So this idea that we can change the momentum of an object is important. Now, if I notice that this is change momentum and this is change momentum, if I put these two things together, I end up with this idea that you could kind of relate all four variables at once. The force times the time is equal to the mass times the change in velocity. Okay? Does that look good? One year, this kid's like, that looks like fat mav. I'm like, I suppose it does look like fat mav, although, okay, sounds good. And this, I think this thing is a really good way to understand the world around us. Let me show you what I mean, and we can get a better sense of it. So let's say you're driving down the road. Okay, let's say you're driving down the road and you're approaching a stop sign. So you need to come to a stop, true? So basically, you and your car have a bunch of mass, and you need to change the velocity. Let's say you're going at like 25 to 0, so your change of velocity is going to be 25, right? There's a couple different ways to stop your car. Could you press really hard on the brakes? You could, right? Could you press really softly on the brakes? You could. How is your stopping going to differ if you press hard on the brakes versus soft on the brakes? What's going to be different about those two ideas? What's that?
When you press harder, you're going to stop faster.
So she's right on the money. Now, you say stop faster, but what you mean is stop in less time.
Yeah.
Right? That is exactly correct. She says, look, if you jam on the brakes, what happens is you apply a large force and your stopping time is small. But what if you apply a small force? Then what happens?
Slow down and
You're still slowing down, but you're slowing down over a much longer period of time. So there's it's called an inverse relationship between force and time. Larger force would be smaller time. Larger time would be smaller force. Does that make sense to you? Why is this useful? Why are we talking about it at all? Great question. Because so much of your world is constructed to take advantage of this idea. Let me show you what I mean. What's this? So you make your way up. Stay on the diving board, contemplating your life choices. So there's a couple ways to get down. One way to get down, just jump in the water, right? No big whoop. I'm gonna jump in the water. That seems pretty good. The water's gonna splash. I feel really good about that. Does that sound good? What's another way to get down?
Calm down a lot.
You could jump down on the concrete. Which of these is better for you? Jumping into the water or jumping on the concrete? Which is better for you?
The water.
Yeah, jumping in the water is way better. Why?
It's solid. Yeah.
You're from the North Store?
Mm-hmm.
What were you doing in the North Store?
Working it?
Oh, well, that's fun. North Store. I like it because it's on receipt paper.
Like a handwritten note.
Where is everyone?
There are some seniors that are gone. Jacob is on a college visit. Liz and Jacqueline are up north on vacation.
I was,
Roland is still at home. Jennifer's just absent. So there are people around, but, okay. So, which of these is better for you? You want to jump in the water instead of jumping on the concrete, true? Why? What's the difference?
Concrete is solid. I want to keep.
Yeah, concrete is very solid. See, the thing about this is, yeah,
Never mind.
no, go ahead.
The water is at a lower level than the concrete is.
Yes, that is true. But why did if you had a choice to jump from the high dive into the water on the concrete, which is better for you?
How high up is the high dive?
High enough that you're going to break some stuff if
Oh,
you
yeah,
fall.
Well, I thought it was like, you know how like if you're fast enough, water is like basically a solid when you hit it.
So that's something that they say, but it's never as solid as solid,
Right.
right? I mean, it's never as solid as solid.
Mm.
And so here's the difference here, is that when you jump off of here, basically, you're going to go from however fast you're moving to 0. So your mass, you're going to change your velocity. Let's say you hit going at 20 miles an hour. You're going to hit and you're going to go from 20 to 0. Okay? If you jump onto the concrete, the time you stop is going to be very small, which means the force on you is going to be very large. But if you jump into the water, are you going to be able to stop in a longer time as you go into the water? Oh, totally, right? So this one, you have a much smaller force because the stopping time is much larger. So, listen, yeah.
I have the safest option that hurts no one, just go down the ladder.
I don't think they let you go down the ladder, do they?
I don't know.
I haven't been to a park with a high dive in a lot of years. The last time I was at a park with a high dive, I think it was probably 4 or 5 years ago. We went to the city park. One of my kids' friends was having a party at the city park. And we went there, and my oldest loves, he likes to show off a lot. And so he'd never been on a high dive before. He just went up there and just jumped off like it was like he'd done it a ton of times. And the next time he went up, he's like, just went and just did a flip off of it. Like it was no big deal. Just did a front flip because he knew people was watching. So, listen to the words correctly. jumping in the water is safer because it increases the stopping time to decrease the stopping force. It increases the stopping time to decrease the stopping force. Does that make sense? All right, Rob, stand up a second. Rob and I are going to do a quick demonstration for you guys.
Uh-oh.
All right, can you catch?
I can try.
That's good enough for me.
Can't catch time.
Well, we're going to see what happens. I have a light bulb that I'm going to throw to you. Okay? Are you ready?
Yeah.
Do you think you can catch it?
Yes.
I have confidence in you. Ready?
Yeah.
All right. Throw it back. All right. Catch it gently. Very nice. All right. So, thank you so much. Great job. Did you notice the motion with which we caught the light bulb? What did we physically do when we were catching it?
Cradle.
Yeah, we call it cradling, right? You give with it, you cushion the catch. Yes? All of that is 100% correct. And the reason we do that, it's my favorite thing, okay? The reason we do that thing is because we are increasing the stopping time to decrease the stopping force. Does that make sense? All right, so what if I were to climb up on here and jump off? I'm just going to jump off. All right? I'm either going to land and bend my knees like a normal person, or as I'm in the air, I'm going to lock my legs nice and straight and land like that. Which of those do you think is better for me? Of course, right? Why is it better? Why is it better?
It'll hurt less.
Why? That's right. It's absolutely going to hurt less. Why is it going to hurt less?
It takes more time.
It decreases the stopping force.
Absolutely, right? This is a nice tag team up here. They said, look, if you bend your knees, you increase the stopping time, which decreases the stopping force on you. Exactly. So here's what you guys are going to do. I've given you now 5 different examples. You need to come up with an example of your own where we have increased the stopping time to decrease the stopping force, usually so something is safer. Does that sound good? All right. Check with your neighbor now. Come up with your example. I cannot wait to hear them. Do that right meow. Ready, there, Luke? What?
Yellow.
Well, let's go. What do you think? There's infinity examples. Infinity. Everybody has to come up with their own individual. Luke, did you come up with one?
It's been like 30 seconds.
It's what?
It's been like 30 seconds or something.
Is that not enough time?
No.
Keep thinking. Luke, did you come up with one? All right, we'll come back to you. Lila, what do you think?
So like when you're sprinting, you don't just like immediately stop, you kind of like jog and then stop.
Because it hurts your knees less, right? I actually think this is a great example. I'm going to take it to the extreme though. Have you ever been to the gym at North? What do they have on the wall behind the backboard?
Isn't there like a cushion?
They do. They exactly have cushions behind there, right? Because if you're like running, you go for a layup, and let's say you forget to stop after that and you have to run into the wall. Are you going to rather run into the brick wall or the cushions?
Cushions.
The cushions, why?
Hurt less.
It hurts less. Why does it hurt less?
Increases your stopping time to decrease your the force.
Absolutely. Natalie's right on the money here. She's like, look, run into the pads. You increase the stopping time, which decreases stopping force. Yes?
I wish they had that at Parcells, because we were doing track and there was no cushions in the back, and they were like, hey, let's try long jumping and jump on the cushion. Let's not put a cushion on the wall and you're jumping towards the wall. And I went a little bit too fast. I ran
Right in the wall? There you go. They needed it. But, so this brings up a great example, right? When you long jump, what do you jump onto? You jump onto the sand, right? One, so they can mark how far you went, but at the same time, is it softer on your butt when you land? Of course, because the sand is going to be softer, which means you have more force and less time. Okay. Natalie, what do you think? Do you have a good example for us?
Like yellow lights, so like in between green and red lights, so you have like time to slow down beforehand.
I suppose, right? Like it's like this example,
And,
right?
like, in theory, yeah.
No, that's a fun example. Yes.
Well, like, I kind of have an example. It's not like something being cushioned, but just if you're like throwing a ball, you know, if you want it to not have as much force, you throw it soft.
So that actually, so you're using the same idea, but in a different way. So this is what you're doing. You're saying force, time, mass, change in velocity. So what you want to try to do is you want to maximize how fast you're throwing the ball. This is what Major League pitchers do. You want to maximize the change in velocity. So there's two things you can do. You can make the force bigger, or you can make the time bigger. Think about Major League pitchers. You ever seen Major League pitchers? They have one thing in common. They're all tall. Did you know this? Why are Major League pitchers all tall? Because taller people have longer wingspan, have longer arms, which means that when I'm throwing the ball, if my arm is longer, it's in my hand for longer, which means that I'm applying the force for more time, which would give you a bigger change in velocity. So, right conceptual framework, but I'm interested in this increased force, or increased time, decreased force. Lewis, what do you think? Yes, please.
Pulling the brakes on your bike.
Yeah, like if you're riding down, you can either do a large force and stop suddenly, or you can do a small force and stop over a long time. Yep, it's a great example. Rob, what do you think?
Kind of stumped.
What's that?
Kind of stumped, I can't really. I'm trying to think of one.
Luke?
Seat belts and cars.
Yes, absolutely. Right? Why are there seatbelts in cars?
So that if your car comes to a sudden stop, you don't get flung forward.
So if you're in a car and the car's going like 35 miles an hour, what are you doing? Are you also going 35? Yeah. If your car hits another car and comes to a stop, are you still going 35? Yeah. So you could either, if you have your seatbelt on, right, you're going to hit the seatbelt. Now seatbelts don't feel very stretchy, but they're a lot stretchier than the windshield. Okay? But what do we have in cars now? We have airbags. What are airbags for? So this, anytime you're going to cushion something, this is what we're talking about. The cushioning of the airbag increases stopping time, which decreases the stopping force. That's what's so cool about it. Luke, great example. Anybody play lacrosse? Lacrosse players? No?
No.
When you play lacrosse, if you want to receive a pass in lacrosse, what do they teach you to do with the stick? You got to give with it as you catch it, right? The reason is that when you give with it, it increases the time and decreases the force, right? And by doing that, it doesn't pop out. If you just held it like this, you'd have a bigger force, it would bounce in and out. Why do you wear helmets in football? Because in a collision, you want to increase the time and decrease the force on your brain. Right? So that's why helmet in football are all padded on the inside, which is good. You ever see a high jumper or a pole vaulter? What do they fall onto? Onto big mats, right? You don't need the mat there. You could just go over and land on the ground. But that would hurt more because the cushions, the pads, increase the stopping time, which decreases the stopping force. I've done some outdoor rock climbing in my time, which I love to do. And if you've ever been to a rock climbing gym or seen a rock climbing rope, they're not like bungee cord stretchy, but they're stretchy compared to steel cables. Because if you fall, you want that thing to stretch out to increase the time and decrease the force on you. A steel cable's much stronger, but that thing's going to stop you in an instant. And it's going to slice you in half. That doesn't sound good, does it? So this is like the thing I want you to know. Okay? Like, I think the most important thing, even from this class, is that so much of our life is dictated by this increased stopping time, decreased stopping force. Right? Let's say you go home and you're exhausted from a long day, and you go in your bedroom, and all you want to do is flop down on the bed, right? What if your bed was made of concrete?
It would hurt.
Why? Because if you flop down onto it, you'd have a small time and a large force on you, true? You want a nice long time and a nice small force so it feels comfy on you. All right, how's that sound? Good? Okay. I want to start something today that is a wrap-up of what we did last week, but we're like done with the unit, so I want to make sure that we have some practice so that we can assess next week sometime. All right, so this is called Momentum Homework 2. Okay. And we did some of this last week with the carts as they were hitting together and bouncing or sticking together. Now remember, our understanding of momentum is its mass times the velocity. That's how you get the momentum of an object. Let me go through and do the first one for you. I want you to copy it down on your sheet also. Okay? All right, Rob, will you read it for us? What's it say?
That?
Number 1.
Oh. In a freight yard, a train is being put together from freight cars. An empty freight car coasting at 10 meters a second strikes a loaded car that is stationary, and the cars couple together. Each of the cars has a mass of 3,000 kilograms when empty, and the loaded car contains 12,000 kilograms of canned soda, a year's supply for the physics class. With what speed does the combination of the two cars start to move?
Okay, so we have a red car and a blue car. The red one is empty. Okay. The red one is empty. And so let's put up the values of the things we know. For example, it says the mass of this one was 3,000 kilograms. And its speed was 10 meters per second.